My name's Steve Strauss. I'm a professor in the Department of Forest Ecosystems and Society at Oregon State and director of the OSU Outreach and Biotechnology program. It's my pleasure to welcome you to this lecture tonight. So this is the fourth of 5 lectures in what's our 7th year of the Food for Thought lecture series, sponsored by the OSU College of Agricultural Sciences and the College of Forestry. Its mission is to bring leading scientists and scholars to speak directly to the public on urgent issues of environment, biotechnology, and food production. The environmental threats facing the world are immense, as I think you all know. And many people are passionate about the environment, either because of their love and adoration of it, or because environmental changes threaten their economies or very existence. Unfortunately, some of the biggest problems that we face do not have easy solutions. Contrary to the common rhetoric we hear that we can simply go green or go natural and all will be fine. Can green instincts, politics, and ideologies in fact lead people and governments in the wrong direction with disastrous environmental consequences? When and where? Given the immense complexity of these issues, vested interests everywhere due to economics or ideology, how can we sort it out? Our speaker tonight, Mark Lynas, is one of a rare breed of writers who have the combination of broad knowledge, clear thinking, and courage to be able to help us navigate and possibly have to right the big environmental ship. As a passionate youth, he vandalized research with GMO crops at night, but had the courage to re-examine the science and change his views. And in doing so, of course, alienated himself from nearly all of the environmental community in Europe. In 2010, he was featured in a TV documentary and news article in the UK titled, "What the Green Movement Got Wrong, a Turncoat Explains." One of Mark's strongest interests has been on climate change, particularly in communicating its severity and the importance of taking bold action to deal with it. His books include High Tide, News from a Warming World, published in 2004, and 6 Degrees, Our Future on a Hotter Planet, published in 2007, for which he won the prestigious Royal Society Prize for Science Books. 6 Degrees also became a TV hit for National Geographic, whose program 6 Degrees Could Change the World, voiced by Alec Baldwin, has been watched by tens of millions around the globe on the National Geographic channel and has been translated into 22 languages. In his most recent book, The God Species, Saving the Planet in the Age of Humans, which is also the subject of tonight's lecture, Mark discusses the vast impact of humans on the planet. He explores 9 planetary boundaries that we are threatening to violate and our responsibility to take bold steps to avoid them. Please help me in welcoming Mark Lynas to Oregon State University.
Thanks, Steve. I thought I told you not to mention the vandalism. You know, I'm here with the support of the US Border Agency, or whatever it's called, but it may not be forever. Anyway, it's great to be here in Oregon, not least because I can go back home to England and in the full knowledge that there's somewhere out there which is grayer and wetter and darker and more miserable looking in winter than even my hometown in Oxford. So thank you, everyone, for that. Now, I'm going to start with a long view here. And that's just to remind ourselves that our planet, this is a fact that you often don't think, our planet's been a living planet for far longer than it's been a dead planet. 3.7 billion years ago, life began. We still don't know how. Richard Dawkins has a different view from the Bishop of Oxford. They were arguing about this just the other week. But as far as I'm concerned, it's still a mystery about how life got going. But it's persisted all this time, despite the sun heating up by 30%, due to this miracle of emergent self-regulation. That's what the hippies used to call Gaia. And in polite society these days, we call Earth system science. Anyway, somehow or other, life has got itself involved in all of the major cycles that keep this planet habitable: the carbon cycle, the water cycle, the oxygen cycle, the sulfur cycle, over eons of geological time. Now, us Homo sapiens have only been around for a few 100,000 years at the very most. This is our evolution. These ups and downs here are the swings in temperature during the last ice age. And actually, I think we only emerge as a fully modern Homo sapiens in this last part here with the emergence of civilization and settled agriculture. And look how stable the temperatures are. This is the Holocene. And this is what's different. There was these huge roller coaster swings. One of these, it was so cold that humans were reduced to just 1,000 people. We almost went extinct. So we've had something of a comeback since then. There's 7 billion of us on the planet, and our evolutionary success story is so profound that we're even now entering a new geological era named after ourselves called the Anthropocene, which is pretty good, eh? You know, we've come from prodding anthills with sticks in just a few 100,000 years to constructing a digital global communications network. So well done, human beings. Round of applause for any humans in the audience? No? No, great job, people. There's a small fly in the ointment, though, and that's that in the process of doing this, we've had to capture between 1/4 and 1/3 of the entire photosynthetic productive capacity of the Earth. And as byproducts of this evolutionary success, we've begun to raise the temperature of the entire Earth system. We've reduced the alkalinity of the oceans. We're altering the chemistry of the atmosphere, increasing the albedo of the surface of the planet, changing the distribution of fresh water, and destroying many of the species that share this planet with us. And so to try and figure out how we can manage the planet most successfully, a team of scientists, including luminaries like James Hansen from NASA, Nobel Prize winner Paul Crutzen, led by Johan Rockström from the Stockholm Environment Institute, came up with this term called planetary boundaries. And the idea is that as planetary managers, the god species, if you like, we've got to figure out how to manage our own impact on the planet so we don't push the Earth system beyond certain tolerance thresholds. So this is a fairly obvious conceptual drawing. The threshold's there somewhere in the middle. We don't know where it is exactly. There's a zone of uncertainty. But once you push over from the zone of stability, you can imagine in terms of climate, this is the Holocene temperatures where it's nice and stable. Vroom, we go over into something completely different. And once you've fallen off that safe zone, there might not be any way back. So we're looking potentially at a much, much hotter world, to take the climate example. What does that mean? And could we ever get back to a more stable climate? Now, I don't want to start, though, with climate change. I want to talk, first of all, about biodiversity. Possibly because I think this is the most important boundary of all. You know, we've poisoned, outcompeted, or simply eaten so many other species in their entirety that the Earth is now in the throes of its worst mass extinction event since the end of the Cretaceous 65 million years ago. And I really don't think you can overstate the urgency of this problem. Every year, the red list of endangered species gets longer and longer. 1/4 of mammals, 1/3 of amphibians, 1/6 of birds, 1/4 of warm water corals, and 1/4 of freshwater fish are already threatened with extinction. And it's not just entire species either. The global abundance of vertebrates fell by 1/3 over the last 40 years. That actually means there's 1/3 fewer wild animals on the whole of the planet, which is really quite astounding. And another thing, every single day, there's more human babies born than the entire remaining population of all the great apes put together. That's bonobos, chimpanzees, gorillas, orangutans. So does it have to be a zero-sum game? Do we have to wipe out so many other species in order to be so successful ourselves? I'm not sure that we do, and I'm not sure either that this one ape, ourselves, has the right the moral right even to capture so much of the planet's productive capacity to the detriment of other species. And I think the science shows very clearly as well that we need to retain the complexity in the biodiversity in ecosystems if the planet is to remain biologically productive and successful and resilient as a living system as it has done over so long. So hence the proposed boundary, which we've already overshot very significantly by as much as 2 orders of magnitude as to how it's proposed. So how do we do something about that? Well, I think we've got to figure out ways to integrate nature into our productive economy. The problem is if we don't put any monetary value on nature, and we don't, a lot of people are worried about doing this for moral reasons, then it has no worth. So I think we've got to look at things like payments for ecosystem services, even biodiversity offsets. You know, if you're doing a big project and you're going to destroy some habitat, then you've got to create new habitat elsewhere. And all told, we're only talking about a few tens of billions every single year, so this isn't big money. Now let's move on to climate change. There's a lot of people who say that global warming stopped in 1998. It also stopped in 1973, 1977, 1986, if you look at these graphs, 1995 and 1998. Of course, if you add all these periods of global warming stopping together, you get a rather nice upward trend of warming. And that's essentially what's undeniably been going on. And of course, if the planet was cooling, like the Republican Party says, I understand, it would be actually very difficult to figure out a physical mechanism for how this can be happening. We know that the Earth's in energy imbalance. We know that greenhouse gases are building up in the atmosphere, and we know that that's the cause of it. So where's all this heat going? You can't destroy heat. That's the first law of thermodynamics. We also know that we don't know everything about the way the climate system works. We don't know the precise magnitude of all the various feedbacks, positive and negative. And the computer models definitely do get some things wrong. The most egregious error the computer models have got wrong so far is that they underestimate the very rapid rate of disappearance of the Arctic sea ice. Now, to save the Arctic from disappearance, we will need a boundary of 350 parts per million in the atmosphere. We're now at 391. This is to retain the integrity of the major ice sheets, in other words, to constrain the rate of sea level rise over the longer term as well. As you probably know, there's a campaign group out there called 350.org. Shout out to them. They're doing a great job. 350 ppm, by the way, is no joke. It means the entire human economy being carbon neutral by mid-century and carbon negative thereafter. So we've got to make this transformation within 40 years. Now, I don't know anyone who has a program for how we can achieve that, but I think we've got to throw every single tool in the book at that problem, and I'll get back to that. I want to move on to another boundary first. This is nitrogen. Now, here's an interesting story. At the turn of the 20th century, a lot of eminent scientists in Britain and elsewhere were very concerned about the prospect of feeding humanity, given the diminishing supply of natural fertilizer that could be extracted from the deserts in Chile. However, they didn't retreat into a kind of Malthusian peak oil type gloom. Instead, they set themselves a challenge and the scientific world for solving the challenge entirely through the use of technology. I'll give you a quote from William Crookes, who was president of the British Association. In 1898, in a famous speech, he said, "As mouths multiply, food resources dwindle. It is the chemist who must come to the rescue of the threatened communities. It is through the laboratory that starvation may ultimately be turned into plenty." That's right, a techno-fix. How unfashionable it is. But he was right, and within less than a decade, or actually just over a decade, by 1912, these two German gentlemen had solved the problem, which is why you know who they are, and why you can shout out to me right now who these two guys are. This is a little quiz, a bit of interactive stuff for you. Not you. No, not you. Someone else. Haber Bosch, there we go. Fritz Haber on the left, Karl Bosch on the right. Fascinating what they managed to do, not least because the synthesis of atmospheric nitrogen was primarily used for munitions in the First World War. So killed a lot of people before saving a whole lot more. Anyway, today, there we are, they got Nobel Prizes as well for feeding humanity. Today we use something like 120 million tons of nitrogen per year. The boundary is proposed at 35, so we've got a long way down to go. The problem being that all of this nitrogen is essential to keep humanity fed. In fact, it's statistically true that half of all of our bodies are synthetic in the sense that the protein in them comes from ammonia fixed in fertilizer factories. And the fact that we're using so much nitrogen is a problem because it runs off into watercourses. You get very large-scale dead zones. It's something like 20,000 square kilometers of the Gulf of Mexico on an average year is now a marine dead zone, and there's something like 400 of these dead zones around the world. So to protect biodiversity from this problem, we've got to somehow do something about the amount of nitrogen that is running off into the oceans. Now, one thing we can do is to take a leaf out of William Crook's book from the turn of the 20th century and look for a techno-fix. What could we do that would enable crops to use nitrogen more efficiently? Well, I'll come back to one later on. To give you a hint, it's something that the Greens really don't want to swallow. It's something Steve mentioned earlier. But I first want to move on to I want to go through all the boundaries. There's 9 of them, so I'll try and speed up a bit. Land use. Why can't we solve the problem by just going organic? Obvious question. Well, because if we did that, we'd either have to watch half the population starve, or we'd have to double the amount of land under production. And land, too, has a boundary, and you've got to factor it into this analysis. Habitat is the most precious resource for biodiversity. That's probably losing so many species. And if we gave up intensive farming, which you want to do if you're organic, we'd lose all the rainforest because there'd be nowhere to grow all of the extra food we'd need. Now, in the Anthropocene, these are your old sort of geography textbook biomes. In the Anthropocene, it's all completely fragmented. We have a different planet altogether, where 85% of it is substantially affected by human activity. And the boundary is proposed as being 15% of the land surface devoted to crops. We're currently at over 12. And remember, we've got to feed 9.5 billion people at much higher consumption levels by mid-century. And that's a huge, huge challenge for land use, almost more than anything else. I think there's an important principle here, which I've certainly seen coming through in the scientific literature, and that's that land sparing is better than land sharing. So you want the most intensive agriculture over the smallest possible area, and basically just leave the rest alone. And the places that you want to leave alone most are the biodiversity hotspots. And it's a really extraordinary fact that on just 1.4% of the world's land, there's nearly half of all the world's species, just in these tiny areas. Those are the bits you really need to protect. Now, perhaps the dumbest idea of all is to use food crops to make biofuels. And I think it really is both a moral and an ecological outrage that 40% of the US corn crop, this is food that could be feeding people around the world more cheaply, is wasted on ethanol production. And tens of millions of people are hungrier today than they would otherwise be because of this pork barrel policy. Now, agriculture needs water as well as land. And globally, 60% of the world's largest 200-something rivers have been fragmented already by man-made infrastructure. That's 800,000 dams, large and small, around the world. And this is an interesting fact for those who say that we can't do large-scale things quickly. Over the last half-century, humans have constructed, on average, 2 major dams per day, and half of those have been in just one country, which is China. Now, the Colorado here in the picture in the Hoover Dam is really, in reality, less of a river than a semi-natural part of a gigantic hydro-engineered plumbing works, which serves 30 million people in the southwest United States. And of course, because of high demand, hardly any of this river reaches the sea on an average year, and that's ruined what was once a thriving and very biodiverse estuarine ecosystem down there in Baja California. Overall, humanity needs a lot more clean water. 1 billion people around the world still lack access to clean water. And in fact, that's the main reason why so many children die early from preventable diseases, because of dirty water. So we need a lot more water, both for drinking and for irrigation. But there aren't unlimited amounts. We've got to share the rivers because these are the main blue arteries of the biosphere. They are the main places where biodiversity is threatened. The extinction rate for freshwater species is 5 times higher than for terrestrial species in general. In terms of the planetary boundary, we're well over halfway there. What can we do about it? Well, we can start by removing the superfluous dams, the ones that we don't need. I think roundabouts here, they've already started doing that, and it's really quite a marvel how quickly the rivers spring back to life, the salmon comes back. It's a fantastic thing. And we need to accept also that hydroelectricity, even on a global scale, is basically maxed out. It's not going to be a major energy source. And don't forget virtual water. That's why eating locally isn't always best. It depends where you are in the world. In Egypt, for example, wheat imports from abroad save 5.8 billion cubic meters of water every single year, equivalent to 10% of the entire national use. So we need to produce food where water is most abundant and where you can do so with minimal ecological impact. By the way, the total world food trade saves 500 cubic kilometers of water per year, and that's a fairly major contribution towards that boundary. Okay, some space left. Now, when I'm going to talk about air pollution, of course, I have to start with a picture of China. That's China there on the right, famously polluted because of all the coal-fired power stations and general industrial activity. In Beijing, they don't announce smoggy days, they announce blue sky days because they're such a rarity. And of course, it's not just in Asia, and air pollution is a significant killer. In the UK last week, there was a report that came out saying that 30,000 early deaths per year are caused by particulate pollution, 4,000 in just in London every single year, and in China it's going to be a lot more. It's statistically a fact that if you had a rational approach to risk, you would evacuate London, or Tokyo for that matter, and move people into the Fukushima exclusion zone. The reason why is because globally the death toll for simple air pollution is estimated at 1.5 million people per year. So that's a Chernobyl every single hour in terms of the death toll. Now, in global atmospheric terms, aerosols generally have a cooling effect. So if we're going to remove that big pall of smog from most of Asia and other parts of the world, we're going to be heating up the planet because all of those sulfate aerosols in particular are reflecting the sun's rays. So here's a geoengineering proposal. Let's take all of that smog, put it into the stratosphere where it can bounce the sun's rays off. I'm not sure that's a great idea. I'd rather do it on computer models for the moment, but you never know. It might need to be something we have in the back pocket. There isn't a boundary put on this because it's simply too damn complicated. To get on to toxics, this is a very dear thing to the heart of any environmentalist. The environmental movement really began with a concern about toxics being spread on the land, in farming in particular, if you think back to Rachel Carson and DDT and stuff like that. And one of the clearest features of the Anthropocene, this new geological era, is that humans have synthesized novel molecules which microbes can't digest, and so they persist for a very long time, and they can have toxic effects. One of the most novel things is plastic. You know, that's not a natural thing. There's plastic pretty much everywhere. The submersibles have photographed plastic bags hanging eerily underneath the Arctic ice cap on the sea floor. In fact, there's one beach in the UK, and this is fairly common now, which is 10% plastic in terms of the granules which are in the beach sand. It's all over the place. And the impacts of a lot of these new substances can be quite catastrophic. I don't know if you've heard about the case of diclofenac. I used to use it for back pain. It's an anti-inflammatory. They use it a lot in cattle, in agriculture, and in India, where they put the cattle carcasses out for the vultures. This affected their livers, and they all died. And something like 99.9% of the vultures have been wiped out in India simply because of this one drug. So you don't know about these things until they happen. And a lot of them also migrate up to the Arctic and accumulate up there. We're talking about mercury, PCBs, flame retardants, things like that, which bioaccumulate in the food chain. A new one which is appearing in the Arctic is cadmium. You find that in solar panels, by the way. People talk about nuclear waste, but we've got to be very careful with solar waste going forward because cadmium has no half-life and will remain toxic forever. These things need to be properly regulated. And by the way, the solar industry in Europe has been trying to exempt itself from any legislation on toxic chemicals, which I think is, what would be a word, regrettable. I do want to talk a bit more about nuclear waste, though, because this would be the boundary that it would come into. You know, people talk about radiological pollution, and it's certainly true that radionuclides are a potential environmental toxin. Although having spent a lot of time looking through, there's a journal even called Radioecology, which looks at the impacts of radiation on nature. I haven't found any example, except for Chernobyl in the very immediate aftermath, where radiation has affected nature in a meaningful way. And now, of course, Chernobyl is basically the Chernobyl exclusion zone, where I've actually been into to film this thing that Steve was talking about, is basically a huge wildlife park. It's full of wolves and bears and all sorts of things. And they don't care about radiation. They're just happy there's fewer humans around. So I think it's probably true to say, and feel free to be offended by this, that the great unsolved problem of nuclear waste has so far not harmed a single living being, human or animal. And if you know of any case in the scientific literature or anywhere else which proves otherwise, let me know, and I won't make that statement again. But so far, no one's been able to find anything. Interesting, huh? Well, here's a boundary number 8, and this is one we certainly can't fix with geoengineering. The problem being that humanity releases, on average, 1 million tons of carbon every single hour. And since James Watt invented the steam engine in 1784, and that ushered in the age of fossil fuels, which is probably the real start date for the Anthropocene, we've dug up and released 500 billion tons of carbon, most of which has gone into the oceans. And because of that equation there, it's making the oceans more acidic, 30% more acidic, or less alkaline rather, since the start of the Anthropocene, since the pre-industrial era. And if we don't halt this trend, we're going to be in a world where tropical coral reefs are dissolving, where calcareous plankton at the base of the marine food chain are disappearing, and that's going to be turning the oceans from blue to green, which has been called the rise of slime. And by the way, there's a whole weight of geological evidence out there, some of which I mentioned in my previous book, where in the distant past there's been gaps in the fossil record where there's no coral reefs. The reason for that was ocean acidification, probably. Large-scale volcanism released a lot of carbon into the atmosphere, and that's one of the main agents of mass extinction, way back through geological time. And I've had a good look through the geology literature, and I can't find a single episode in the last 500 million years, the last 500 million years, where the rate of carbon release, not the magnitude yet, but the rate of carbon release comes anything close to what we humans are achieving at the moment. So even the most cataclysmic super eruption causing the worst mass extinction at the boundary of the Triassic and the Jurassic doesn't come close to our combined power station chimneys and vehicle exhausts. Isn't that an amazing fact? Well done, humans again, eh? There's a boundary there which I won't explain, but we've got 30 or 40 years to meet that one. Not so long. Another quiz for you. Who's that guy? And the clue is in the title and in the picture. Steve, do you know that one?
I forgot, sorry.
You forgot. He's a loyal servant of General Motors Corporation back in the 1920s. And he has 2 inventions to his credit. One is the addition of tetraethyl lead to engines to petrol rather, to stop engine knocking. And the other was the invention of CFCs for refrigeration. And his name is Thomas Midgley. And in the words of historian John McNeill, he probably had more impact on the atmosphere than any other single organism in Earth history. Now, these CFCs initially would have seemed like a miracle because they're completely non-reactive, non-combustible, unlike some of the previous things that were being used for fridges. But that's only in the troposphere. Once they get into the stratosphere, the sun's ultraviolet radiation breaks them apart, you get free chlorine, and that destroys ozone. By the way, here's a good story for you. When NASA first spotted the ozone hole, they assumed it was instrumental error, and they spent several years deleting the data from their records, which showed that this hole was going on. And do you know who put them right? It was the Brits. They had an Antarctic base, and they had the real data, and they got their paper in Nature first. So this is a success story because we were over the planetary boundary for a few years in the 1980s, and now we've come back on the right side of it because of the international process called the Vienna Convention, which later led to the Montreal Protocol in 1987. And I think there's some really good, have I got any more on that? Yeah, so that's what happened after this was signed. This is 1989. This is the production of these chemicals. It goes right down and is almost eliminated by the end of the 2000s. And I think there's several lessons to be gained here. One is that it helps to have the US on side. Believe it or not, officials from the Reagan administration were instrumental in getting this treaty agreed, and the US Senate was the second in the world to ratify it. Imagine if that happened with Kyoto, we'd be in a very different situation to the one we're on today. Second lesson for me is that if politicians set the path, business will follow. Right? That's the right order of doing things. Politicians act first, the government sets the framework, does the regulation, then business comes up with the alternatives. There's this persistent myth that the Ozone Treaty was only agreed once DuPont and the other big corporations had already achieved patents on the substitutes. That's not true. Actually, what happened was that the companies were determined to stop regulation. They're so determined, in fact, they even shut down their research programs so that there wouldn't be any substitutes, so the politicians couldn't point to them. But they went ahead anyway. And then once the incentives had switched around because the regulation was going to be coming in, then the companies had an incentive to change, and they were, they were then going to use the commercial advantage. The third lesson for me is that technical substitutes are nothing to be ashamed of because, I mean, call me a fatalist, but I do believe that if saving the ozone layer had meant permanently giving up not just refrigeration, but maybe even just hairspray, we'd all be wearing dark glasses and a lot of sunblock today, and there would be a very big hole in the ozone layer. So, what's the challenge? The challenge, as I see it, is that we've got to eliminate poverty and bring everyone up to Western levels of consumption by 2050. And we've got to do that within the planetary boundaries. Now, at this point, I'm going to show you one of my fabulous graphs, because I want to show you why GDP, which is quite unfashionable these days, is such an important metric. What I've got here is a graph moving through time. Okay. Oh, I'm still in 2000. That's no good. Now, can you see the pointer here on the screen? On the left-hand here, we have child mortality. This is the year 1800, and I'm going to shift the years forward on this slider here. And all the countries in the world will pop up, and they have the little dots. There's Sweden there. It's the only country we've got any data for in 1800. So you can see what the child mortality was in Sweden in 1800. 381. So more than a third of all children died before reaching the age of 5. This is how life was before the Industrial Revolution really got going. And GDP is 1,100 per person. Now, as I play this forward, you're going to see more dots appear. More countries are going to be coming into the picture. I'll move around a bit so you can see what they are. And they're getting gradually richer as they migrate towards the right. These are all just European countries. That's all we've got data for at this point. But some of the bigger countries are going to come in sooner. There's Russia, still non-communist, so it's doing all right. There's India, so it's a bigger population. That's why it's a bigger dot. But look, they're moving towards the right down here, and child mortality is going down. So they're all moving, and you can see the relationship. There's quite a straight line between them. And this is world development for you here. Back in the 1980s, 1990s, that was the AIDS crisis when they all went down there. So what I find really interesting here is anyone guess what that country is at the top, which has the worst level of child mortality still? You won't get it. It's Chad. But look, 209. Remember, Sweden was 380 back in 1800. So even the worst off country in terms of child mortality is better off than the richest country in the world was in 1800. And it's this relationship which I find really interesting, because it shows how dramatically related wealth and child survival are. And of course, I'm a parent of 2 children. I think we could all agree that it's the worst thing that happens to you in your life if your child dies. And that should not have to happen to anyone. Child mortality is also very related to food supply, as you might expect. Linear relationship there too. Play this forward. There's China, India. They're all food supply varies in different years, but basically everyone's migrating down to there. Look at these on the right. So US people are eating too much, and child mortality isn't great, 7.9. You'd be much better off living in Luxembourg, where it's right down at 3. So this is just to illustrate for you how important some of these relationships are and why it's such an important challenge for us to be able to solve world poverty, as we must do, but also keep within the planetary boundaries, which are, as I hope I've demonstrated, real. Okay. Now, one of the ways we can do this, I might go back and show you, is through cities, right? And there's a question here for you. India, 2030, how many cities of more than 1 million people? Come on, it's easy. 68. How about China? Take a guess, anyone? More than 100, 221. So we're in an increasingly urbanized world, and that's a good thing. In 2008, there was a very important milestone crossed, which was that more people were living in urban areas than in the countryside for the first time ever. Here's one. Fertility changes during urbanization. And there's not such a clear relationship, but generally speaking, countries which have a higher urban population, which is down here on the bottom. So there's Belgium, 93% urban, Japan, 43%, but they've all got fairly low fertility. This is back in 1960. Play this forward, I think you'll see all the countries sort of just dropping in terms of fertility and going over towards the right as they get more urbanized as well. So there's a strong relationship there, and that's because families in cities don't need to be so large. You don't have the same issues with subsistence, and having lots and lots of children is a cost rather than a benefit once you're in a town. And there's more economic opportunities and more access to healthcare and family planning. So urbanization and this growth in GDP have diffused the population bomb very successfully indeed. What else do we need? We need the sustainable, it's nice to be back up here, intensification of agriculture. Now, we live in a world where 13% of the population is still undernourished, by the way, so they don't have enough food, if you remember that graph. And we've got to improve productivity as fast as possible. Big debate about how to do it. And some people come up with some very stupid things indeed. Anyone heard of this woman, Vandana Shiva? Have a look at what she's written there. I'm indebted to Stuart Brand for discovering this. This was in a book, so this is from Google Books. And she's very well known for her virulent opposition to genetically engineered crops. And she talked about the spread of sterility. Now, maybe Charles Darwin got it all wrong, but when was sterility a selective advantage? So if you have two sterile parents, they get together and they have more offspring. No, I don't get it. Anyway, so let's talk about someone who does know what he's talking about. Norman Borlaug, father of the Green Revolution. That's why all those dots moved to the right after the 1960s, because people were fed successfully in a way which was never thought possible before. And he spent his final years, he died at the age of, I think it was 95, 96, not so many years ago. He spent his final years campaigning desperately to stop technophobic environmental activists from derailing the genetic improvements in crop varieties around the world, which are needed to keep the Green Revolution going forward. Now, as Steve mentioned, I've changed my perspective, 180 degrees, 360 degrees? I've gone round so many times. From being somebody who I spent years of my life campaigning against GMOs, and I can only say that I feel so ashamed about it that I can hardly bear to talk about it. And we had a conversation earlier on, and I know some of the people who even destroyed some of the crop trials that Steve's colleagues have been working on. And I think what turned me around was becoming interested in science. And I wrote a book about science, climate science, and people told me when I was writing anti-GMO stuff, you've got to hold yourself to the same scientific standards as you do when you're talking about climate change. And it's so far true to say that with GMOs cultivated on 3 billion acres worldwide, there isn't a single substantiated case of health or safety impacts. There was a French ban, the French ban on GMOs was challenged in the court recently, was ruled illegal by France's highest court because the French government couldn't produce any scientific evidence of risk to health or the environment. You know, and if you come into a court of law and the prosecution can't produce any evidence, then whoever's on trial is innocent. Now, the anti-GMO lobby, my former colleagues, repeat a lot of myths, some of which we can talk about later if you like. But perhaps the most pernicious and persistent of all is that the only benefit of biotech is for these big, bad corporations, including, or especially including the devil incarnate, Monsanto. And they seem to assume that farmers are either stupid or very easily duped. that they can't see for themselves. They keep buying these crops, they keep buying these seeds, and they can't see for themselves that they're losing money or they're losing yield. And in fact, the opposite is true. Yields have gone up so much that something like $10 billion a year extra is accruing to farmers because of the GM crops they're growing. And did you know that 90% of the farmers who are growing these crops are in the developing world, and they're growing them for a reason? Let's go on to something that we can all agree is a good thing. And a good reason why you should do carbon offsetting is to stop this kind of thing happening. If you pay a few dollars to mop up a ton of CO2 with a clean cook stove, you can reduce deforestation because they're more fuel efficient, and you reduce indoor air pollution, which I think is way more important than climate change, certainly for this lady, because the levels of toxin in indoor smoke in developing countries where women are cooking indoors like that are hundreds of times World Health Organization standards. This is killing 1.6 million people per year. They're mostly women and children who are in the domestic environment. That's 3 people per minute, 180 people per hour. So please, if you don't already do so, consider carbon offsetting and donating to a project which funds clean cook stoves like that one. How am I doing for time? I can't even see the clock. I'm doing fine.
You're 45 minutes in.
Oh, really? Anyone bored yet? No? Good. I'll stop you getting bored. Let's talk about nuclear power. Now, I think the most important environmental equation in the world is E equals mc squared, because it describes how much energy you can get from nuclear fission. Breaking chemical bonds, so bonds between electrons, releases only trivial amounts of energy compared to splitting the atom. You can get 1,000,000 times more energy from a lump of uranium this size than you could from a lump of coal this size. Now, today it's true that 16% of world electricity comes from nuclear power. And I think it's also true to say that that proportion would be much, much higher had it not been for the anti-nuclear movement, which really got going in the mid-1970s. And with a combination of lawsuits and various forms of relentless campaigning, succeeded in making nuclear power too expensive to be a viable proposition in most parts of the world. And the upshot of all of this is that the world is now dependent on, almost fully dependent on coal for electricity, and getting more so all the time, resulting in tens and possibly hundreds of billions of extra tons of carbon in the atmosphere than would otherwise be the case. And if you think of all the planetary boundaries I've just talked about, that's bad for the climate, it's bad for ocean acidification, for toxics, for aerosols, biodiversity, nitrogen. The list is very long. Now, I'm not saying that nuclear fission is the panacea or has no problems. That would be a bit stupid after what happened at Fukushima, although that is still a non-fatal accident, by the way. Fukushima's reactors were what's called boiling water reactors. They were designed in the early 1960s. And nuclear technology hadn't stood still since then. So this, I think, is the greenest single piece of technology ever designed. And it's a sodium-cooled fast reactor designed here in the good old United States. One variant of which is the integral fast reactor. Another's called the PRISM, which is being marketed by GE Hitachi. And this was designed specifically at Argonne National Laboratories to address all of the problems identified by anti-nuclear activists. And a few of us did some work in the UK, and we looked at the stockpiles we've got of nuclear waste, depleted uranium and spent fuel and so on. And if you feed all of that waste that we've got sitting around in the UK into fast reactors, potentially you can run the whole country at current levels of electricity consumption for 5 centuries, 500 years, simply to get rid and burn up, get rid of the nuclear waste that we've got sitting around at the moment. And in the US, it's 6 or 7 centuries. So you don't need to mine a single scrap of new uranium. You simply reuse what we've already got, which strikes me as being a better idea than putting it into Yucca Mountain or whatever, because actually you've got a huge, huge energy value in the uranium that's already been mined and which has not been used efficiently through the current once-through reactors technologies that we've got now. What else is interesting about this? It has full passive cooling, so you can switch it off, or you can hit it with a tsunami and walk away, switch off the coolant. Actually, you wouldn't want to hit molten sodium with a tsunami, having said that. So you'd build it slightly higher away from the sea. But This is designed on the, from a prototype that was called the experimental breeder reactor, which was built in Michigan, and ran successfully for 30 years. And in fact, they did that, and this was the month before Chernobyl, because I don't think they've done it the month after Chernobyl. But anyway, they switched off the coolant and just walked away. And lo and behold, it shut itself down. I think this is much more interesting than the current generation 3 reactors. I think we should look at being more ambitious and moving to generation 4. And so let's solve the waste problem. Let's say the waste problem is already solved, and we can solve the climate change problem at the same time. Greenpeace is against this. Friends of the Earth isn't sure. Greenpeace doesn't know why it's against it, but they know they are. Here's another thing we've got to get better at, and that's making international treaties. All planetary boundaries are transboundary, right? They cross international borders, and so by definition, they have to be worked at the international level. And this is exciting potentially because it represents our species-level commitment to mobilizing our collective intelligence, which is probably why it's so damn difficult and most of the time doesn't work. And I say that as somebody who spent years, miserable years, on the inside of the climate change process as a representative for a developing country government. So there's processes on biodiversity, which is a bit toothless climate we've talked about. There's a toxics convention, which is actually reasonably successful in Ozone. It hasn't been done too badly. Some of these other planetary boundaries, though, will need to be considered. Certainly haven't been so far. We need processes, I think, for all of them if we're going to manage the planet successfully. Let's talk about the really bigger picture, just to finish off. This is dematerialisation. And this is the idea of using less of everything at the same time as we continue to grow the economy globally. And this is I hope this is a good illustration of dematerialisation. That's all there is on the slide, by the way. Now, at the root of this, there's some fairly basic economics. Now, I only studied economics up to A level. That's the English thing, right? I don't know what that is in the UK, in the US, like 8th grade or something. But do you remember how you have that curve of marginal utility and it levels off? Yeah? It goes up like that and levels off. The point being that the marginal utility of having one fridge when you've got none is very high because then your food doesn't rot. The utility of having 2 is not so high because you're running out of space. 3 fridges, 4. By the time you get to 4 fridges, it's going down because you've run out of space in your kitchen. So the point is that we don't have growth that goes on forever because sooner or later you reach a point of material satiation. It's the same with cars, by the way, already. We've, by the way, seen peak travel already. People are traveling less kilometers than they were every single year. And the same process has begun to occur in many different sectors of the economy, almost unknown, by the way, to a lot of people. In the UK, there's a measurement that the government undertakes called total material requirement. And that began falling even before the recession and even counting for imports. So we were using less stuff even as economic growth was taking place. And that's what dematerialisation looks like. On the other hand, zero growth economics simply doesn't work, There's been very, very eminent economists who've looked at that problem and not been able to make it happen. And actually, as a closet Republican myself, I think we should cherish growth as being the engine of innovation and creativity in a capitalist economy, which I think is the most productive and dynamic social system that's ever been invented, and hopefully will be the one which solves the problems presented to us by these planetary boundaries. Watch this. I think this is a great achievement. This was taken by from the International Space Station. And what it shows for me is how beautiful this planet is. And in fact, in some ways, how it's more beautiful because of the fact that we've lit it up and we've given it extra color, which it never used to have. And perhaps even more so, in James Lovelock's words, if I can remember, that the planet is beautiful because we are alive and we're able to see her with her own eyes. And that's the first time that's ever happened. No species have ever had that property before. But that's not quite the end. Very nearly. All right, there we all are. This, so on the original roof of the Sistine Chapel, right? This is, which one's God and which one's, I can't even remember, but, yeah, Adam, that's the other one, yeah. So Anyway, the point is that that's me up there, that one now, and this is you, and this is all of us, and that we have to run the planet as if we were gods, because both of those hands in the picture belong to us. And it's up to us to determine what the temperature of the planet is going to be in decades to come, and it's up to us to determine the chemistry of the atmosphere and the oceans. And we've got to decide how much of the living natural world to protect as we go forward. Now, I want to finish by saying fairly unapologetically, although I am a bit sorry about this, that I remain an optimist. And I don't think I've got any scientific basis for this. I think it comes down to personal, faith, really. And the difference between optimism and pessimism is that optimists have faith that we'll be able to do things tomorrow to solve problems that we can't do today, whereas pessimists think that we'll have less options tomorrow and we won't be able to solve the problems even that we've got today. And actually, I'm not a scientist, as you can probably tell. I'm really a historian in terms of my training. And I think that the lessons of history are on the side of the optimists. So I'll stop there. Thank you very much.